Hello and welcome to another Java tutorial. In this tutorial, I'm going to talk about some special functions, and these functions appear all the time in physics and engineering problems. And the reason we call them special functions is because these are typically the functions that we cannot express them in terms of elementary functions, or at least we cannot express them in terms of a finite number of elementary functions. And by elementary functions, I mean typical functions like sine, cosine, log, exponential, these kind of functions. These functions typically come from differential equations that appear in engineering, for example, the wave equation or the heat diffusion equation. And again, sometimes most of the time we express them in terms of an infinite number of a series, which is a summation of infinite number of elementary functions. That's why they don't have a closed representation based on the elementary functions. Then one of the most important functions is Bessel functions. So what are Bessel functions? Bessel functions are the solutions to the Bessel ordinary differential equation. What is the equation? This is the Bessel equation. X squared y double prime plus xy prime plus x squared minus nu squared times y equals 0. So this nu is the parameter of the Bessel equation or Bessel functions. And obviously this is a second order differential equation, so it must have two linearly independent solutions, and we call them J nu of x and y nu of x. So y nu sometimes is called the Weber function or Neumann function, and J nu is called the Bessel function of the first kind. Y nu is called the Bessel function of the second type or the second kind. Y nu is sometimes also shown or denoted by n sub nu, but here I'm using the notation of y sub nu. Now, a very special case, and it's indeed very special and very important because that's the case that typically happens in the wave equations when we express it in a cylindrical coordinate system, is the case when nu is an integer number, and in those cases we typically use n instead of nu. N or m, these are integer indices, right? So Jn of x and Yn of x. And this differential equation obviously has a singularity at x equals 0, because when x is 0, these coefficients go to 0. So the behavior of the coefficients or the terms of the differential equations is impacted by setting x to 0. And it turns out that J nu of x doesn't have any singularity at x equals 0, and these are the plots of J nu of x for positive x and integer nu values. So J0 is this function, and all of these functions show some sort of oscillatory behavior. J0 always starts from 1. Other J's, J1, J2, they always start from 0. And then J0, you see, as x progressively increases, we end up with an oscillatory behavior. And there is no surprise that we expect that when x is very large, we see some sort of sine and cosine function. And we do indeed see that behavior, but the amplitude of the oscillations eventually dies off. And as we will see, it's actually 1 over square root of x, the amplitude, and the phase or oscillation is basically sine and cosine. So that's exactly the behavior that we expect just based on observing the behavior of these J functions. Okay, so but y nu, the Neumann function or the Bessel function of the second kind, they all have a singularity at x equals 0. And the singularity brings them to minus infinity, okay? So this is y0, again, it starts from minus infinity, and we do the oscillation and the amplitude of the oscillations after getting away from the singularity is 1 over square root of x, and the phase is sine or cosine, right? So y0, y1, y2, etc. Now, how do we find the numerical value? And the obvious answer would be to solve the differential equation, but that doesn't seem like a very efficient way of doing it. So, right? And besides, when we need to solve the differential equation, which we already know how to solve differential equations, we need initial conditions, right? So the first question would be, what are the initial conditions? And this is a second order differential equation. So we need two initial conditions: the value of the function j nu or y nu at x equals 0, and the value of the derivative, the first derivative, j prime and y prime, right? Now obviously from this you see the main problem with the y nu in this approach, because y nu has a singularity. So the initial condition cannot be that, okay, at x equals 0, y nu at 0 should be minus infinity. We cannot numerically solve such a initial condition, right? So this is not the best way to go about solving differential equations. However, if we go this route, solve the differential equation, and we saw it in our discussion on the solving the ODEs that if we solve a second order ODE, not only we get the function, but we also get the derivatives of the function, which is a plus. So if we try to solve this for these j nu functions, which are well-behaved functions, then we do get the not only j nu but also j nu prime. Well, it turns out there is a relation between j nu prime and the values of the j nu function. So it turns out we do not actually need to calculate j nu prime directly. We can calculate two j nu functions with different nu values and then relate them to the j nu prime, and we will see that later. So what we're going to do here, instead of solving differential equations, as I mentioned, we see that for x very large, there is some asymptotic behavior, right? And asymptotic behavior is the function somehow becomes sine and cosine in terms of the oscillations, and the amplitudes go down by some sort of 1 over x or some similar function, and as it turns out, it's 1 over a square root of x. So what we want to do is, instead of solving the exact equation or trying to come up with something in different ranges for x values, we try to use asymptotic expressions for these, because asymptotic expressions are always expressed in terms of elementary functions, right? So let me just write it here, based on elementary functions. And because it's based on elementary functions, then it's very easy or very efficient numerically to calculate those asymptotic functions, all right? So here's the first approach for calculating the Bessel functions of the first kind for integer values. So for integer indices, j0, j1, j2, and or negative values, j minus 1, j minus 2, or y minus 1, 1 minus 2, etc. So in this case, the parameter of the Bessel equation is an integer number, and we already know that jn doesn't have any singularity at x equals 0. j0 at 0 is 1. j0 prime at 0 is 0. These are the observations by just looking at these plots. For n positive, jn at 0 is always 0, so j1, j2, j3, even j minus 1, j minus no, etc. They're all 0 except for j0. And here's the relation, which only holds for integer indices. J minus n if n is negative or positive. Let's call this positive. Then minus n becomes negative. So a negative index of j is minus 1 to the nth power jn. Later we see that when this goes to non-integer indices, j minus nu, this minus 1 becomes basically a complex number. And instead of having, because minus 1 has a complex representation, which is e to the j pi. And we already know that e to the j pi n is just minus 1 or plus 1. But if n is a non-integer number, e to the j pi nu is actually a complex number, right? So in that case, some very interesting things happen, and it's very well worth it to look at it, right? So we will definitely look at it, and it's definitely worth it to look at the cases when this becomes a complex number. But for now, we already see that if we calculate the Jn for positive n, we already know the value of j for negative n values, right? And this shows that, okay, for even indices, j0, j2, j4, etc., the jnx function is an even function. It has an even symmetry, or it's symmetric about the x equals 0 axis. And for odd indices, j1, j3, etc., they are odd functions or anti-symmetric. All right. Now this another equation also applies for x negative. So if we know the value of jn of x for positive x, again it's related to the value of negative x related to the value of the positive x of the function with -1 to the n, right? So for integer n, when index is integer, whether you reverse the sign of index or the sign of x value, you get -1 to the n power. All right. And again, this shows that basically, again, j1 and j-1 are connected, and j1 is basically an odd function, right? So j0, j2, j4, etc. even functions, j1, j3, j5 odd functions. All right. And j-1 is just minus j1. All right. So for integer indices, so I'm going to highlight this here again. So only when the index of the Bessel function is integer, we can use these integrals. And we will see what happens when this index is not integer anymore. But for now, let's assume that this is an integer index, jn, n could be 0, plus minus 1, plus minus 2, etc. Jn is given with a very nice closed form integral, 1 over pi, integral from 0 to pi, cosine of x, sine of theta minus n theta d theta. So theta is the parameter of the integration, and eventually the result of this is a function of x, right? But as you can see, we cannot express this result of integration with an elementary function or a finite number of elementary functions. What we can do is to expand this cosine in terms of its Taylor series, which is an infinite number of functions, and then integrate term by term, because the Taylor series of cosine is absolutely and uniformly convergent, right? And we end up with an infinite series for jn. And then we have to find the limit of that series for each given value of x, right? So that's one approach. But obviously the simplest approach here is to directly integrate, do a numerical integration of this function. Whatever the function is, we can always calculate because it's a definite integral, it's a proper integral, so we won't have any problem just numerically integrating. One question is this the most efficient way of calculating Jn? And the answer is no. And again, that's because based on the series expansion, we can always find the asymptotic series for a small x, large x, and those prove to be more efficient in terms of numerically calculating the functions. All right, so yn is similar with jn. It does have a proper integral, 1 over pi 0 to pi sine of x sine of theta minus n theta d theta. So what jn was cosine, yn is sine. But we have to somehow include that singularity, right? We said that at x equals 0, yn has a singularity, so it should go to minus infinity. So we have 1 minus 1 over pi 0 to infinity e to the nt. Remember, n is the index of the function and is integer. Plus minus 1 to the n e to the minus nt e to the minus x sine hyperbolic or sinh of t dt. And again, t is the parameter of integration. And the result of this is eventually a function of x. Now what you can see immediately is that if x is negative, then e to the minus x sine hyperbolic of t is positive, right? This minus x becomes positive, and there is a very high chance that this integral diverges. So this representation is only valid when x is positive. But then we said that for yn, when is integer, there's exactly a similar relation holds for negative index and positive index, and they are related by this minus 1 to the n. right? And the same relation holds for the yn when you have negative x and positive x, right? So basically what we do, this is the representation for positive x, and when we have negative x, we just multiply it by -1 to the n. All right. So the problem here is, as we can see, we have an improper integral which goes from 0 to infinity. So we have to use some tricks or some truncation, because we cannot go from 0 to infinity numerically. So we have to go from 0 to some large number. And we will try to look at what is a good number here so that we get a good convergence. All right. So let's go and implement the Jn of x in Java. Remember, we're doing the integer index right now, and this integral works for integer indices for now. So Jn of x is 1 over pi 0 to pi cosine of x sine of theta minus n theta d theta, and theta is the parameter of integration. So a very simple way of doing it is Jn. We define a Jn function, returns a double value. The index is integer n, and the x can be any double number, right? Positive, negative, doesn't matter. We define our integral function. T goes to 1 over pi cosine of x sine of t minus nt, and t is the parameter of integration. And then our integral 1D object, we call it integral Jn. Set integral function, find Jn. Why are we doing this? Because for different x values, as we change x, the integral function changes. For example, if I have 0 or I have 1 for x or 2, the format of the integral function is changing, right? So we have to redefine the integral function and change the integral function in our integral object. And then we can use any of the methods that we developed: forward rectangle, backward rectangle, center rectangle, Simpson, trapezoid, or accelerate them with Romberg integration, which was a fourth order Richardson acceleration. All right. Now here I'm using Romberg and Simpson, and this will give us very good accuracy based on the order here. Order is basically the number of sub-intervals that the integrator calculates. Basically the integral object divides the interval 0 to pi to n sub-intervals, and n is basically the order, how many sub-intervals to use. Because remember, integration is just a summation, and in each sub-interval we pick a value or associate some sort of value to the function, or a combination of different values of the function gives us a single value for each interval. And then we sum them by multiplying those values with delta x, right? And all these methods, I'm not using a quadrature method here, I'm just using a simple uniform partitioning. And here's the example. And obviously this integration depends, the accuracy or the convergence depends on this order. And this is the first thing we're going to look at. So we're going to create a sequence whose parameter is this order, and try to see what happens when we increase the order, how fast we get to a good result, right? The convergence speed. So the way I do it is I create a Bessel function and create some numbers, let's say from 0 to 4t and 1000 points, and f0, f1, f2, f3 arrays are just evaluating the Bessel for Jn, integer index. N is 0 for all these x values, and then J1, J2, J3, and then plot them all together, right? Create a chart, blue color for J0, red color for J1, green color for J2, and black color for J3, and then plot them. All right? And as we expect, we see this oscillatory behavior. J0 is 1 at x equals 0. Other J functions, J1, J2, J3, etc. must be 0, right? And let's try to go to Eclipse and look at, first plot them, and then try to look at the convergence, all right? So in the Eclipse, I have created a new project, special func, and I have this Bessel function integration. The reason I have a Bessel function and a Bessel function integration is that, as I mentioned, the actual implementation of Bessel function evaluation is typically with power series, not with the integration. That's why I created a separate class for integration. So we have these integral function 1D, func j inf, func yn, func yn inf, and for integer indices we only use this function func jn. And then we have the integral class. The order by default is 300 subintervals. In the constructor I just initialize them to random numbers. And then here's my integration approach for calculating jn. So the index is integer, x can be any double value, positive, negative, 0, doesn't matter. We have to define the integral function. I'm using a lambda expression, and the reason is that the integral function depends on x. So changing x will change the integral function. That's why we have to redefine it each time we evaluating at a specific x. And then we set this as the integral function for the object. And then instead of Romberg and Simpson, because a center rectangle requires less calculation, so it's going to be faster, right? Order. And all right, so let's create a test class. So in the test package, I'm going to create a test class, test jn integration. All right, I want to have a main method. And in the main method, I'm going to just have test1. And in the test1, as I mentioned, I'm just going to plot them. So public static void test1. And in the test1, I'm going to create a Bessel function integration, Bessel new Bessel function. So I want to use the integration equation, this 1 over pi 0 to pi integral of cosine. And then double x is mathutils dot linspace from 0 to let's say 50, 1000, and then double j0 is let's call the array func apply, and we want to have t goes to Bessel.jn, and this is the integer. I believe let's look at the method again. We have the integer and double. That's what we're looking at right now. I want this to be a and t, and then I apply them to the x array. All right, and then I'm going to create my chart, my figure. Let's call this this is the MATLAB chart, fig.plot x and j0, and I'm going to plot it with b, the 2f, the line width, and the legend or the label is j0 of x. And then I'm going to render the plot, and then basically legend on, and then fig.show with the exit flag. Run it. It doesn't show the figure because I'm on a Mac, so I have to go to run configuration. In the VM arguments, I have to remove this check. All right, this is our Bessel function j0. It starts from 1. It's basically horizontal, so the derivative is 0, and we see this oscillation. Well, let's time it. So I'm going to create a timer, new timer, and it's from the mathlib util timer. So, and then timer.start, and then after I do the evaluation of the array, timer.stop and sysout timer. 51 millisecond to calculate 1000 points. Now let's see what so let me just keep this. So 50 millisecond roughly. But let's see what happens if we use the Romberg on Simpson with the order of 300 subintervals. Now it takes much faster, and it turns out that it actually gives us pretty much the same accuracy. So Romberg, a better integration approach doesn't really help that much in terms of the accuracy. That's why we can set instead of Romberg on Simpson, we can just use the center rectangle. And remember, center rectangle has an error order of delta x squared. Simpson had an order of delta x to the fourth, and then when we accelerate with Romberg, we get delta x to the eighth. And here, delta x to the second order error is good enough for us. And the other thing that I want to point out here, so let's maybe create the test 2. And in test 2, what I'm going to do, so let's put this here. So public static void test 2. So in test 2, I'm going to again create this Bessel, all right? And then I'm going to just evaluate it at, let's call it double val Bessel dot jn for int, and let's evaluate it for j0 at a large number, let's say 20. All right, 20 is double value. So this uses by default order of 300, right? But then we have this method to set the integration order. So double basically index or order. Or what I'm going to do, actually, it's better to create a sequence. So this is our sequence, segjn at 20. And then n goes to what? So what I want to do here, I want to take my Bessel, set integration order to n, right? So I'm changing the integration order, and then return Bessel jn at order 0 at 20. All right, so I'm calculating basically j0 at 20 with different number of sub intervals or order, right? So we want to see how accurate that integration is, and this is complaining because this method is defined for int, but in our sequence interface, if you recall, we're defining based on the long. So we have to do an explicit casting here for n. All right. So I'm going to create my chart, or maybe let's evaluate the function. So double index new double, let's say 1000, and double jn vals is new double index dot length, and for int I equals 0, len is index dot length, and I less than len I plus plus. What we're going to do is basically index at I mean, it's always easier for me to define the index as a double. It's just I plus 1. So we want to start with one sub interval, and then jn vals at I is just we take that sequence, evaluate it at I plus 1. All right, so we are calculating j0 20 at 20 for some number of sub intervals, which sets the accuracy of the integration, right? And then we have our MATLAB chart, fig new MATLAB chart, and then fig.plot index and jn vals, fig.render plot, fig.show with a exit. And this val was not necessary to calculate, but so let's remove this. So again, what I'm doing here, I'm creating a sequence that evaluates j0 at 20 with different number of sub intervals for the integration, all right, for the center rectangle. And this should show us how the convergence happens. And as you can see, originally we have some inaccuracy. Integral tries to stabilize, and eventually after 18, 19, 20 sub intervals, we are pretty much there, right? So an order of 300 is really not that necessary for this case. So we can actually lower the order. Instead of 300, remember the default, I just set it to 300 because center rectangle is fast enough. But we actually do not need that very high 300 order. We can even evaluate it at 40, 60 subintervals. And again, but the problem is that, as you probably guessed, if we increase, let's go from 20 to 100, then the integral stabilizes at a later point, right? So we get a good convergence after, let's see, how many, 70 or 80 subintervals. And again, 300 is still seems a little bit large. But let's look at the case when we try to use the Simpson method. So if we compare the two, so the center rectangle was stabilizing at about 60. Simpson is stabilizing at about 60. I mean, there's not much difference here. All right, maybe the amplitudes of error is a little bit smaller, but besides that, there's not much difference in terms of the convergence. Now let's do a Romberg on Simpson. All right, as you can see, this has much worse situation in terms of the values for the oscillations. But then again, it is still stabilizes at 60. So there's really no value. It appears that there's no value in using a better integration approach instead of just staying with the simple center rectangle. So we're going to choose that. And back to 20. If now, so let's run this again for J0 at 20. All right. Now let's increase the order, J5 at 20. So J5, this stabilizes at about 16, 18. This one was also stabilizing at 18. So it appears that there's not much difference in terms of the order. We can go even higher, so J10. So it's more about the x value instead of the index. So here we are stabilizing again at 20. So the 300 is really not that necessary. And reducing 300, again, even to 100, this can help us maintain the accuracy, but basically speed up the calculation by a lot, right? Now, if I go to 200, this is a very large value for Bessel function, and we will probably see that, yes, so it stabilizes at a very later point at about 120. So here 300 seems a reasonable number. So what we can do, we can divide the evaluation into separate regions, x between 0 and let's say 50, x between 50 and 200, and x greater than 200. And based on that, we can set the order of integration, this number of subintervals. That can also be some sort of optimization in terms of the efficiency of numerical calculation. Okay, this was the first lecture on Bessel functions. I hope you enjoyed it. Please stay tuned, and I'll see you in the next one.